Our universe is a place of constant motion. Planets orbit stars, stars cluster into galaxies. These celestial dances are not random but follow the intricate laws of physics, creating a cosmic ballet that has been ongoing for billions of years. Galaxies themselves move through the vast expanse of space. They drift, collide, and merge, forming ever larger structures in a dynamic and ever-changing universe. This movement, this fundamental characteristic of the cosmos, is governed by a powerful force: kinetic energy. Kinetic energy is not just a concept, it is the driving force behind the motion of every object in the universe. Understanding kinetic energy is key to comprehending the universe's dynamics, from the graceful orbits of planets to the explosive collisions of galaxies. These interactions shape the very fabric of our cosmos, influencing everything from the formation of stars to the creation of black holes. Kinetic energy is the energy of motion. It is what keeps planets in their orbits and drives the expansion of the universe. Without it, the cosmos would be a static, lifeless place. It's the energy an object possesses due to its movement. The faster an object moves, the more kinetic energy it has. This principle applies to everything from the smallest particles to the largest celestial bodies. From the smallest particles to the largest celestial bodies, anything that moves carries kinetic energy. This energy is a fundamental aspect of the universe, influencing how objects interact and evolve over time. This energy is fundamental to how objects interact, shaping the universe as we know it. The collisions and interactions driven by kinetic energy lead to the formation of new stars, planets, and even entire galaxies. The study of kinetic energy in space helps us understand the formation of our solar system. By examining the motion of celestial bodies, we can trace back the history of our cosmic neighborhood and uncover the processes that led to the birth of our sun and planets. It explains the destructive power of asteroid impacts. When an asteroid collides with a planet, the kinetic energy released can cause massive destruction, shaping the surface and even affecting the planet's atmosphere and climate. It also allows us to chart the courses of spacecraft as they journey through the cosmos. By understanding kinetic energy, we can predict the paths of these man-made explorers and ensure they reach their destinations. By understanding kinetic energy, we unlock secrets of the universe's past, present, and future. This knowledge helps us piece together the story of the cosmos, from the Big Bang to the present day, and even make predictions about its ultimate fate. In this exploration, we will delve into the concept of kinetic energy. We will examine how it influences the motion of objects, from the tiniest particles to the largest galaxies, and how it shapes the universe we live in. We will explore its significance in the cosmic realm. Kinetic energy is not just a scientific concept, it is a key to understanding the very nature of our universe. Join me as we unveil the power of the universe in motion. Together we will journey through the cosmos, uncovering the secrets of kinetic energy and its profound impact on everything around us. Kinetic energy is calculated using a simple yet powerful formula. Ke equals 1/2 times mass times velocity squared. In this equation, Ke represents kinetic energy, m stands for the object's mass, and v represents its velocity. This formula is a cornerstone in the study of physics, providing a clear and concise way to understand how objects in motion carry energy. This formula reveals a fundamental truth. An object's kinetic energy is directly proportional to its mass and the square of its velocity. This means that both the mass of the object and its speed are crucial in determining how much energy it possesses while in motion. Let's break down this relationship. Firstly, mass plays a crucial role. The greater the mass of an object, the more kinetic energy it will have if it is moving at a given speed. This is why massive celestial bodies like planets and stars have immense kinetic energy. A heavier object moving at a certain speed carries more kinetic energy than a lighter object moving at the same speed. This principle can be observed in everyday life as well as in the vast expanse of space. Think of a bowling ball and a tennis ball rolling towards you at the same speed. The bowling ball, with its greater mass, will have a more significant impact due to its higher kinetic energy. The bowling ball, with its greater mass, will have a more significant impact. This is a simple yet powerful illustration of how mass influences kinetic energy. Secondly, velocity has an even more dramatic effect on kinetic energy. The speed at which an object moves can exponentially increase its kinetic energy, making velocity a critical factor in the energy equation. Doubling an object's mass doubles its kinetic energy. This linear relationship is straightforward and intuitive. However, doubling its velocity quadruples its kinetic energy. This is because kinetic energy is proportional to the square of the velocity, making speed a powerful multiplier in the energy equation. This exponential relationship highlights the incredible power of speed in the universe. Objects moving at high velocities can carry enormous amounts of kinetic energy, far surpassing what their mass alone would suggest. Consider the awesome spectacle of a comet streaking across the sky. Its incredible speed, combined with its mass, gives it tremendous kinetic energy capable of creating spectacular displays as it interacts with the sun's energy. Its incredible speed, combined with its mass, gives it tremendous kinetic energy, capable of creating spectacular displays as it interacts with the sun's energy. This interaction not only produces stunning visual phenomena, but also serves as a powerful reminder of the dynamic forces at play in our universe. The universe is teeming with objects possessing kinetic energy. Our own solar system provides a dynamic showcase. The planets, including our Earth, orbit the Sun at various speeds, each carrying kinetic energy proportional to its mass and velocity. Earth, for example, orbits the Sun at an average speed of 67,000 miles per hour. Beyond our solar system, asteroids and comets hurtle through space. Asteroids, rocky remnants from the early solar system, vary greatly in size. Some are small, like pebbles, while others are hundreds of miles in diameter. Regardless of their size, their movement gives them kinetic energy, which can have significant consequences if their paths intersect with Earth. Comets, often described as dirty snowballs, are icy bodies that release gas and dust when they approach the Sun. This release creates their characteristic tails, which can stretch for millions of miles. Comets, like asteroids, carry significant kinetic energy due to their speed. This energy can lead to spectacular displays as they interact with the Sun's gravity and radiation. Section 4. Observing kinetic energy in space asteroids and impacts. One of the most dramatic ways we observe kinetic energy in space is through asteroid impacts. These celestial bodies, often remnants from the early solar system, travel at incredible speeds, sometimes tens of thousands of miles per hour. When they collide with a planet or moon, the results can be catastrophic, showcasing the raw power of kinetic energy. These events vividly illustrate the immense power of objects in motion. The energy released during such impacts can be equivalent to millions or even billions of tons of TNT, depending on the size and speed of the asteroid. This energy is not just a theoretical concept, but a tangible force that can reshape landscapes and alter climates. When an asteroid collides with a planet or moon, its kinetic energy is released in an instant, creating an explosion of heat, light, and shock waves. The immediate aftermath includes the formation of a crater, the ejection of debris, and the generation of seismic waves that can be felt across vast distances. The heat generated can ignite fires, while the shock waves can cause widespread destruction. The impact of the Chicxulub asteroid, believed to have wiped out the dinosaurs 66 million years ago, serves as a stark reminder of the destructive potential of kinetic energy. This event, which marked the end of the Cretaceous period, led to the extinction of nearly 75% of Earth's species. The asteroid's impact created a crater over 90 miles wide and released energy equivalent to billions of atomic bombs. This massive asteroid, estimated to be about 6 miles wide, slammed into Earth with unimaginable force. The collision released an enormous amount of energy, vaporizing rock and sending molten material high into the atmosphere. The resulting dust and aerosols blocked sunlight, leading to a dramatic drop in temperatures and a nuclear winter scenario that lasted for years. The impact released energy equivalent to billions of atomic bombs, triggering widespread fires, tsunamis, and a global dust cloud that plunged the planet into darkness. The fires would have consumed vast areas of forest, while the tsunamis devastated coastal regions. The dust cloud, by blocking sunlight, disrupted photosynthesis, leading to a collapse in food chains and the mass extinction event. Even smaller asteroids can have significant effects. While they may not cause global extinctions, their impacts can still be devastating on a local or regional scale. These smaller bodies, often referred to as meteoroids when they enter Earth's atmosphere, can explode with the force of a nuclear bomb. In 2013, a meteor, a smaller fragment of an asteroid, exploded over Chelyabinsk, Russia. This event provided a stark reminder of the potential dangers posed by even relatively small celestial objects. The meteor, traveling at a speed of about 42,000 miles per hour, entered the atmosphere and exploded with a force estimated to be around 500 kilotons of TNT. This relatively small object, estimated to be about 66 feet in diameter, released energy equivalent to about 440,000 tons of TNT. The explosion created a bright flash, a powerful shock wave, and a series of sonic booms that were heard for hundreds of miles. The force of the explosion was enough to damage buildings and infrastructure over a wide area. The airburst shattered windows over a wide area, injuring over 1,000 people, a testament to the kinetic energy carried even by smaller celestial bodies. The Chelyabinsk event highlighted the need for better monitoring and understanding of near-Earth objects, as even small asteroids can pose significant risks to human populations and infrastructure. Section 5. Velocity's power, amplifying kinetic energy. As we've seen in the formula for kinetic energy, velocity plays a crucial role in determining an object's energy of motion. The relationship between velocity and kinetic energy is exponential, meaning that even small increases in speed can lead to significant increases in kinetic energy. Imagine two identical asteroids hurtling through space. One asteroid travels at 10,000 miles per hour, while the other travels at 20,000 miles per hour. Although the second asteroid is only traveling twice as fast, it possesses 4 times the kinetic energy of the first asteroid. This concept is crucial for understanding the potential danger of near-Earth objects. Even relatively small asteroids, if traveling at high speeds, can possess enough kinetic energy to cause significant damage upon impact with Earth. This is why space agencies around the world are constantly monitoring the skies, tracking potentially hazardous objects and studying ways to deflect them, if necessary.